Okay, let's unpack this, because if you break a bone, the surgeon is going to use a titanium screw to put you back together.
Right.
And that screw is, well, it's likely smaller than a green pea. It has features measured in fractions of a millimeter. And if the machine that cuts it is off by, like, the width of a human hair.
Yeah, the implant could just fail entirely inside your body.
Exactly. And we just kind of assume that piece of hardware is perfect when it arrives in the operating room. But today we're taking a deep dive into the industrial engineering sources behind extreme medical manufacturing.
Which is a fascinating space.
It really is.
Yeah.
Specifically, we're looking at the critical role of the B-axis Swiss lathe. So our mission today is to uncover the mind-boggling precision required to create the tiny, flawless hardware that, well, literally holds people together.
Yeah, and what's fascinating here is that it is the absolute definition of extreme manufacturing. When you look at the source material on these medical bone screws, the geometric requirements are just, they're staggering. We are looking at components that are often shorter than 10 millimeters.
Which is tiny. I mean, that's incredibly small.
It is.
And it isn't just a simple threaded cylinder, right?
Yeah.
Like, these screws have complex Torx recesses for the driver, locking holes bored right through the sides, variable thread pitches.
And incredibly thin walls.
Yeah, thin walls, all hovering right around the 1 millimeter scale. So making something that tiny is hard enough on its own.
Absolutely.
But the engineering literature points to a massive operational hurdle called one clamping.
Right, one clamping.
Essentially, once a machine grabs the raw titanium bar stock, it is an absolute golden rule that it cannot let go until the screw is 100% finished.
And the physical reality of machining dictates that. I mean, in manufacturing, you have something called a datum.
A datum, okay.
Yeah, which is your absolute zero. It's as the reference point from which every single dimension is calculated.
So like the start of the thread or the center of the cross hole.
Exactly. The depth of the drive recess, all of it. So the moment you unclamp a partially finished screw, move it, and then clamp it into a second machine to finish it, you introduce a datum transfer error.
Because in the physical world, it's mathematically impossible to clamp a microscopic piece of metal a second time with the exact same zero-point alignment.
You just can't do it.
It kind of reminds me of translating a complex technical document multiple times.
Yeah.
Like, you translate a manual from English to French,
Right.
and then you take that French text and give it to a Japanese translator, and
Yeah.
then take the Japanese and translate it back to English.
Oh, that's a great way to look at it.
Yeah, after one jump, it might be legible.
Yeah.
But by the third transfer, you've totally lost the fidelity of the original meaning.
Yeah.
But in this case, losing fidelity means a locking hole and a thread pitch are, microscopically out of alignment.
And that misalignment ends up permanently embedded in a patient as femur, which is, yeah, it's a huge problem. But beyond dimensional accuracy, one clamping is heavily driven by strict surface integrity and chemical requirements.
Chemical requirements. Wait, for a piece of metal.
Yeah, absolutely. Before a medical implant is ready, it has to go through passivation.
Okay, what is that?
It's a chemical bath process that removes free iron from the surface and creates a protective oxide layer.
Oh, to make it highly corrosion resistant.
Exactly.
So it doesn't rust inside the human body.
Precisely. But for the passivation chemistry to work perfectly, the surface of the titanium must be utterly pristine.
Oh, I see.
Yeah, every time a robotic arm or a human hand touches that screw to move it to another machine, it introduces microscopic clamp impressions or, residual oils, airborne particles.
Just from handling it.
Still from touching it, yeah. By finishing the entire screw in one single clamping operation, you keep the surface chemically uncontaminated and physically flawless right up until the cleaning phase.
Okay, that makes sense. But here's where it gets really interesting, because the constraint of one clamping sets up a total mechanical nightmare.
It really does.
If we aren't allowed to move the tiny piece of titanium to reposition it for all these complex cuts, like the angled cross holes or flat milled edges, how do we actually carve those bizarre geometries?
Well, the solution detailed in the engineering sources is the B-axis.
The B-axis.
Right. Traditionally, a turning lathe simply spins a piece of metal in a circle while a stationary blade scrapes against it.
Just a spinning block of metal.
Yeah. But the B-axis transforms that standard lathe into a fully flexible turn mill center. It actually rotates the tool head itself around an angular center line.
And the sweeping ranges they mention in the text are incredible, like ranging from 0 to 95 degrees.
Or even swinging fully back and forth plus or minus 110 degrees.
Which is wild. It essentially adds a highly articulated, programmable wrist to the machine.
That's exactly what it is, a wrist.
Right. It works in tandem with standard X, Y, and Z directions to position a spinning cutting tool at practically any angle. So instead of removing the workpiece to drill an angled hole, the B-axis tilts the drill bit itself and dives in.
It sounds elegant on paper, but machining at those variable angles introduces intense physical stresses.
Well, yeah, looking at the physics here, I don't understand how this is even possible without just destroying the material.
Because it's so small.
Right. We're talking about raw bar stock, titanium, or even softer biodegradable polymers. That is 0.5 millimeter to 2 millimeters thick.
Which is nothing.
0.5 millimeter is essentially the thickness of mechanical pencil lead.
Yeah.
If I take a piece of graphite and I push a tiny drill bit into it from the side at a 45-degree angle,
It's going to snap.
the sideways pressure snaps it instantly. How does the lathe not just deflect and snap a 0.5 millimeter rod?
That is where the specific anatomy of the Swiss-type lathe becomes critical, particularly something called the sliding guide bush.
The sliding guide bush. Okay.
Yeah. In a conventional lathe, the metal is gripped at the back by a chuck, and it sticks out into the cutting zone like a diving board.
Oh, I see where this is going.
Right. If you apply a lateral force to the end of a thin diving board, it bends, chatters, and ultimately shears off.
The vibration alone would destroy the tolerance.
It would. It completely ruins it. But a Swiss-type lathe fundamentally changes how the material is held. The sliding guide bush acts as a continuous, rigid support mechanism.
Oh, okay.
To use your mechanical pencil analogy, if you hold a pencil by the eraser and try to write firmly, the tip wanders everywhere.
Yeah, you have no control.
Exactly. But if you grip the pencil mere millimeters from the graphite tip, you have total control. The guide bush supports the metal bar just fractions of a millimeter away from where the B-axis cutting tool makes contact.
So it's bracing the metal at the exact point of impact.
Yes.
Neutralizing the lateral force of the B-axis.
And by neutralizing that deflection, the B-axis is able to optimize the tool path. And this isn't just about getting the geometry right, you know?
It's not.
No, it's about controlling the residual stress left in metal. When you force a cutting tool through titanium at a suboptimal angle, you leave microscopic stress fractures.
Just from the brute force of it.
Yeah, tension in the thin walls of the screw. By utilizing the B-axis to slice into the material smoothly at the perfect calculated trajectory, you preserve the metallurgical structure.
Oh, wow.
Which directly translates to superior fatigue performance, ensuring the implant won't fail under the cyclical load of a patient walking.
So the mechanics of the one-clamping solution literally extend the lifespan of the implant?
They really do.
But logically, there is a gaping hole in this process.
Oh!
Yeah, even if this highly articulated B-axis wrist can twist and cut every conceivable angle on the front of the screw while the guide bush holds it steady, it is still attached to a long bar of raw titanium.
Right, it's still part of the main bar.
Eventually, you have to sever the finished screw from the bar.
You do.
So when you cut it off, how do you finish the back end of the screw without violating the one-clamping rule?
That is where you utilize a dual spindle architecture. The machine doesn't drop the part to be picked up later, right?
Okay.
It actually executes a synchronized handoff while the part is still inside the machine.
The sources outline a main spindle and a sub-spindle, right?
Yes.
So the main spindle handles all the front side operations we just covered. The variable threads, the drive recess, the angled holes.
Exactly.
Then, just before the cutoff tool severs the screw from the bar stock, the sub-spindle comes in, grips the front of the screw, and holds it tight during the cut.
But the mechanics of that grip are extraordinary. I mean, the main spindle is spinning the raw material at thousands of revolutions per minute.
Wait, it's spinning while it grabs it.
Yes. To execute the handoff without damaging the partially finished screw, the sub-spindle has to advance and match that rotational speed perfectly.
Oh my gosh. It's less like passing a baton on a track and more like a midair refueling between two fighter jets.
That is exactly what it's like.
If the main spindle is spinning at 4,000 RPM, the sub-spindle has to catch it perfectly at 4,000 RPM.
Right.
If there is even a fractional mismatch in speed or alignment when it clamps down,
It would instantly shear the microscopic threads right off the screw.
just rip them right off.
Absolutely. And once that synchronized grab is complete and the part is severed, the sub-spindle retracts with the screw, exposing the unfinished back end for final machining.
But wait, so is this B-axis like an octopus? Can it cut the front piece on the main spindle and the back piece on the sub-spindle at the exact same time?
No, it's physically one B-axis cannot cut both at the exact same instant.
Okay, that seemed like a bit much.
Yeah, it serves one machining zone at a time based on the machine's tool bank layout.
Oh, I see.
But parallel production still happens.
Uh,
So while the B-axis is darting over to finish the back of the previous screw on the sub-spindle,
right.
the main spindle is working on new stock.
But doesn't that rapid whipping movement introduce the exact vibration and wear we are trying to avoid?
Well, it would if the machine lacked the mass to dampen it. These lathes are built on incredibly dense cast iron beds specifically to absorb the kinetic energy of a tool head whipping between zones.
Oh, so the heavy iron just absorbs the shock.
Exactly. And functionally, the B-axis operates on independent computer channels. It only serves one zone at a time, but it never really stops moving.
Meaning the spindles don't wait for each other.
Correct. The main spindle has already fed out fresh bar stock and is using stationary tools to rough out the front of screw number 2.
Wow.
The B-axis darts back and forth seamlessly, optimizing cycle times by up to 30%. And in some complex multi-machine comparisons, yielding a 3 to 5 times speed gain.
And it solves what the engineering literature calls the drop problem.
Yes, the drop problem is huge.
Because if you don't have a sub-spindle, when you cut that 1 mm screw off the bar, it drops into a parts catcher.
Which is a disaster.
Finding a micropart in a tray, cleaning it, and trying to execute a secondary loading where a robotic arm tries to pick up a tiny, slippery, complex screw and put it into a second machine perfectly aligned is nearly impossible.
You risk scratching it, introducing massive datum errors, and frankly, mixing batches.
And batch contamination in medical manufacturing is a regulatory nightmare.
It'll get your line shut down instantly. The dual spindle handoff entirely eliminates the drop, ensuring absolute traceability from the raw bar to the finished part.
Okay, so the B-axis solves the complex geometry, and the dual spindles solve the dropping and the one clamping problem.
Right.
But realistically, adopting these multi-axis dual spindle machines requires a massive capital investment. We are talking about highly specialized, incredibly complex technology.
Oh, they are not cheap.
Why would a manufacturer take that financial hit when traditional, cheaper lathes technically work?
Because the initial capital expenditure is actually offset by the elimination of fixed-angle live tools.
Which are the dedicated mechanical attachments traditional machines use to drill angles.
Exactly. So without a B-axis, if an implant requires a locking hole at a 30-degree angle, the manufacturer has to purchase a special tool holder permanently geared at 30 degrees.
Oh, I get it. It's like buying 10 different golf clubs, each permanently locked into a specific angle for a specific swing.
And if the next design requires a 45-degree hole, they buy a 45-degree tool.
That sounds incredibly inefficient.
It is, and those fixed-angle attachments are notoriously expensive. Furthermore, they require constant maintenance. Their internal gearing introduces vibration.
Which ruins the surface again.
Exactly, and they take up valuable physical real estate inside the machine's tool envelope.
So the B-axis, paired with a standard high-frequency spindle, functions as one universal magical golf club where you simply program the wrist to change the angle for you.
That's a great analogy.
You use one tool, the machine tilts it to 30 degrees to drill, then tilts to 45 to mill a flat.
It offers unparalleled flexibility. But if we connect this to the bigger picture, engineering is always a trade-off.
Okay, what's the catch?
The engineering sources are careful to point out that a B-axis, utilizing a high-frequency spindle, operates at extreme speeds. We're talking between 30,000 and 80,000 revolutions per minute.
80,000 RPM.
Yes. And they achieve a runout, which is the rotational wobble of 1 micrometer or less.
Which is perfect for carving microscopic torque slots or tiny crossholes.
Yes, but high-frequency spindles inherently lack torque.
Oh, because speed and torque are inversely related in these small motors.
Exactly. To spin a tool at 80,000 RPM, the motor mass must be very low to reduce inertia.
Right.
But low mass means low electromagnetic force. If you try to use that high-speed, low-torque spindle to plow through dense titanium for heavy roughing or deep slotting, the motor will just stall.
Or the tool will deflect.
Right. Therefore, the B-axis is a magic bullet that makes heavy-duty tools obsolete. It is a strategic optimization for light, complex micro-features.
While the lathe still relies on rigid, integrated power tools for the heavy material removal. Which brings us to the actual physical output of the machine, because these specifications are staggering.
They really are.
The sources note that a capable B-axis Swiss lathe can hit linear positioning near 0.03 millimeters and in indexing accuracy, how precisely the B-axis tilts of 0.001 degrees.
For context, 0.003 of a millimeter is roughly a fraction of the width of a human red blood cell.
So what does this all mean? It's imperceptible.
It is.
But the sources explicitly warn that brochure specifications are essentially meaningless on the shop floor.
Oh, absolutely.
A machine capable of 3-micron linear positioning doesn't automatically output a perfect medical implant. The validated part tolerances they actually achieve are closer to plus or minus 0.005 millimeters.
Which is still microscopic.
Still microscopic, yeah. But the literature states these tolerances are impossible to hold without mastering thermal drift. I understand that cutting titanium creates intense friction and heat. But how does the ambient temperature of a factory, or a slight change in coolant temperature, ruin a piece of solid metal?
This raises an important question about the undeniable physics of thermal expansion.
Okay.
Heat causes matter to expand, and cold causes it to contract. When you are operating within a margin of error of 5 microns, a fluctuation of just 2 or 3 degrees in the ambient room temperature will cause the massive cast iron frame of the lathe itself to microscopically expand or warp.
Wait, really? The giant iron frame warps from a 2-degree room change?
Yes.
So the absolute zero datum point we talked about earlier actually shifts physically as the day gets warmer.
Exactly. Furthermore, if the cutting fluid isn't perfectly chilled and regulated, the titanium bar stock absorbs the heat from the 80,000 RPM cutting tool and swells.
Oh, no.
Yeah. If the machine carves a dimensionally perfect locking hole while the titanium is thermally expanded, what happens when the completed screw goes into a parts bin and cools down to room temperature?
The metal contracts, the hole shrinks, and suddenly the part is out of tolerance and has to be scrapped.
Precisely.
It changes the entire math of the operation. You aren't just programming a tool path, you're programming a thermal management system.
You are. This is why manufacturers implement rigorous, hours-long machine warm-up routines before cutting a single piece of medical stock.
Just to get the machine up to operating temperature.
Yes. They map the thermal drift of the machine via software, allowing the computer to dynamically adjust the zero point to compensate for the heat of the spindle motors.
And there is a geometric vulnerability with the B-axis itself, right? The sources mention that the angular error at the pivot point gets amplified.
Yes, that's a crucial point. An indexing error of 1/1000th of a degree at the B-axis pivot might seem completely irrelevant.
Right.
But the further the cutting tool extends from that pivot point, the larger the linear error becomes at the tip. It's like aiming a laser pointer.
Oh, yeah. A microscopic twitch of your wrist moves the dot on a distant wall by several feet.
Exactly.
So the tool overhang must be kept as short and rigid as physically possible.
Precisely. And even if a manufacturer masters the thermal drift, minimizes tool overhang, and utilizes the dual spindle handoff, perfectly dimensional accuracy is only half the battle.
There's more.
Oh, yeah. A screw that is mathematically flawless in its dimensions is still a catastrophic failure if the micro-burr control isn't validated.
A microburr, like a little flake of metal.
Right. If a tiny sliver of residual metal breaks off a thread inside a patient bloodstream, the implant fails.
So the machine is just a platform, but the manufacturing process is a delicate, interconnected ecosystem.
That's a beautiful way to put it.
The guide bush must perfectly match the bar stock to avoid friction. The coolant must be thermally regulated. The tool wear must be mapped. It is a symphony of kinematics, material science, and thermodynamics.
It truly is a monument to modern engineering. But as the materials we use inside the human body evolve, the machining challenges are only going to compound.
Which is a fascinating thread to pull on as we wrap up, because the source material briefly notes that the industry is beginning to adapt these Swiss lathes to handle newer biodegradable materials.
Yes, which is wild.
We were talking about advanced polymers designed to provide structural support while a bone heals and then safely dissolve and melt away into the body.
It is an incredible leap forward for patient care. I mean, eliminating the need for secondary surgeries just to remove hardware.
But think about the physics we just unpacked. If a manufacturer has to fight ambient room temperature and software-mapped thermal expansion just to hold a 5-micron tolerance on solid titanium, what happens to precision when the entire medical industry shifts to implants made of materials that are literally formulated to melt?
It's a huge unknown.
If you spin a cutting tool at 80,000 RPM against a biodegradable polymer, does the material begin degrading and melting from the sheer friction and heat of the manufacturing process before it ever reaches the patient?
That is the exact precipice the industry is standing on. How do you aggressively machine a material designed to disappear without making it disappear while you cut it?
Right.
The coolant strategies, the tool geometries, and the thermal management will have to be entirely reinvented.
It's a profound engineering paradox, and definitely something to chew on the next time you think about the microscopic hardware holding us all together.
Absolutely.
Well, until next time, keep diving.